Hello, welcome to this video. We'll go over a solution of some of the questions of the final exam of 2016 of 1EL3. I just try to maybe stress some of the important concepts that you have to keep in mind when you are heading for your exam on Tuesday. So I will focus on two questions in this video, and then I will talk about two more questions in the following video. Okay, so the first question we have, this question here, we have a circuit. It has four loops as shown here. So we have four loops in this circuit, and we would like to calculate the currents I1, I2, I3, and I4. Once we have found these currents, we can do post processing. We need to find the voltage across the resistor R5. So this is resistor R5 here, okay? So once we found the current I2 and we found the current I3, we can see that the current going through here is simply I2 minus I3, and the voltage drop is equal to I2 minus I3 multiplying R5. So this is a very simple calculation. We're also required to do the get the power across the resistor R1, and this resistor R1 here, as shown, it's being shorted out. So this means the voltage across this resistor is zero, and there is no current going through it, and thus there is no power consumed by this resistor. So without even thinking about it too much, we can simply say that the answer to part C is simply zero. Okay, so to start to analyze this circuit, we need to do mesh analysis. Mesh analysis, simply we associate with every loop one current, and then we write Kirchhoff voltage law in every loop, and then we try to solve the resultant system of equations. Of course, for mesh analysis, we have to get rid of all current sources. We can get rid of this current source, and we have to get rid of it. This is 1 milliampere in parallel with 3 kilo ohm, so we can replace it by a battery of value 3 volts in series with a resistance of 3K. This one we cannot get rid of it, and we don't really need to get rid of it because it's not in a branch joined or joint branch between two loops. It's not here. This branch here is a joint branch between third loop and the second loop. This one is the branch related to the third loop alone, and actually it's very helpful. When you take a look at this one, you can immediately realize that I3 must be equal to 2 milliampere, because the current flowing in this part here, which is the current I3, is equal to that current source, which is 2 milliampere. So we really do not need to solve 4 equations, 4 unknowns, but rather 3 equations, 3 unknowns, because the fourth unknown is already known to us. So we start to simplify the circuit. And as I mentioned to you before, whether it's nodal analysis or mesh analysis, don't start to apply the analysis method until you have simplified the circuit a little bit. So we can sum this voltage source, 4 volts plus 2 volts are in series, will give us 1 voltage source, 6 volts. 1K and 2K are in series, will give us 3K. This one here will give us 3 volts in series. 1 volt will give us 4 volts. The same thing is happening here. This is 5 and this is 4, and they are opposing one another, and the result will be 1 volt with this polarity. This is 1K in series 1K. This will give us a resistance of 2K. Once you have done all these simplifications, we redraw the circuit again, and the circuit would look way simpler. And of course, we get rid of R2 because there is no current passing through R2. Any current that will flow in this branch would simply continue in the short circuit and bypass the resistance R2 completely because it's being shorted out. Okay, so if you draw the circuit after you have done all these simplifications, this is how the circuit would look like as shown in the next slide. Okay, so we did the necessary simplifications. We got rid of all the unnecessary component, like the resistance R1 is already gone here. I added the 2 voltage sources here. I added the 2 resistances. I added the 2 voltage sources here. I added they have this same resistance, battery resistance, and I did all types of simplification. The circuit now looks way simpler. I know now from my just looking at the third loop that I3 must be equal to 2 milliampere. So this is given, and they simply have to solve now for I1, I2, and I4. Now to write KVL around this loop here, we'll go around the loop. Negative positive is counted as positive, positive negative is counted as negative. So this is 6 volts minus 3k multiplying I1 minus 3k multiplying I1 minus I2, okay, and you have the last one minus 4 volts is equal to 0. Okay, so negative, positive, positive, negative, positive, negative, positive, negative. So this one will be with a positive sign. All the other three will be with a negative sign. So 6 volts is equal to 3. Okay, the 3 here we have 3k multiplying I1 plus we have also the 3k here. This will appear with a negative sign. So minus 3k multiplying I1 minus I2 minus 4 volt is equal to 0. Or I can simply say that 6 volts is equal to 3k multiplying I1, 3k multiplying I1 minus I2, and we have 4 volt as well on the other side. One thing that can simplify your analysis, if you assume that I1, I2, and I3, I4 are all in milliampere, I don't have to keep on writing kilo ohm. So I can simply say that 6 volts here is equal to 3 I1, okay, plus 3 I1 minus I2 plus 4. I don't have to keep on writing k, or multiplying 10 to the power 3, because I know my answer will be in milliampere. Okay, I can repeat the same thing exactly for the second loop. So negative, positive will be counted positive. So I can simply 4 volts plus 3 I1 minus I2. Okay, negative, positive. This one is also negative, positive, plus 2 volts. This one here is positive, negative. So minus 2 multiplying I2 minus I3 will be equal to 0. Okay, so this will be the KVL for the second loop. So let me repeat this one again. Negative, positive, I'm going to go around in the clockwise direction, and I will count the drop negative, moving from negative voltage to positive voltage as positive. So 4 volts plus 3 I1 minus I2, this drop will have this polarity, negative, positive, so plus 2 volts. This one here I assume to be positive, negative, so minus 2 multiplying I2 minus I3 is equal to 0. So this is the second KVL, okay. The third one, I can do it for this loop here. Third loop, I can simply say negative, positive is counted as positive, okay. And for this one here, I can simply, if I'm assuming that this is I4 and this I3, they are opposing one another, so I will take the polarity with I4. If I take the polarity with I4, is actually good. The drop is going to look something like this. It's not going to be this one here, okay. So just forget about this one here. If I assume that the I4 is greater than I3, then the drop here is equal to 3 I4 minus I3. Okay, so if you go around this loop as well, we'll go in this direction. It doesn't matter whether you go clockwise or counterclockwise, as long as you are consistent in the way you are calculating the voltages. So negative, positive is positive. So 2 volts plus, this is going to be positive here, 3 multiplying I4 minus I3, which is 2 milliampere. Because I4 is flowing like this, so this is positive, negative, and this also will count as a positive drop. So plus 2 I4. This one has an opposite polarity. I'm going this way, okay. So minus 1 volt will be equal to 0. So 2 volts plus 3 I4 minus I3 plus 2 I4 minus 1 is equal to 0. And I don't really to write the fourth KVL for the loop, for the third loop here. I don't like write KVL here because I know already what's I3. I3 is equal to 2 milliampere, and I'm gonna get rid of I3 in the second loop and in the fourth loop and replace it by 2 milliampere. Okay, I will start now to write the equations again, and as you could see, what I redraw the circuit here again, or I copied it from the previous slide just to show you what's happening. So in the first loop, as we agreed, we have this 6 volts is equal to one drop, a second drop, a third drop here. This is all counted as drops because this is negative, positive, while this is positive, negative, positive, negative, and positive, negative. So 6 volts is equal to 3I1 plus 3I1 minus I2 plus 4. If you organize the equation for the first loop, you obtain this one here, that 6I1, okay, minus 3I2 is equal to 2. We go the second equation. We'll go again in the clockwise direction. So we can simply say negative, positive is positive. So when I move from a negative voltage to positive voltage is positive. So this one is positive, this one is positive, this one is also positive, while this one is negative. Okay, so I can simply say that 4 plus 3I1 minus I2 plus 2 minus 2 multiplying I2 minus I3 is equal to 0. And here I got rid of I3 and I replaced it by 2 milliampere. I don't have to keep writing I3. And as I mentioned in the previous slide, I don't write 3K I1 or I2 because I already assumed that all of them will be in milliampere. So I got rid of the 10 to the power 3 with the 10 to the minus 3 of the milliampere. If you organize this equation, of course, you have to go back and reorganize it again and collect coefficients related to I1 and I2. And as I warned you before, you have to put them in order. So I1, I2, and I3. You get this equation here. So now we have two equations. Equations 1 and equation 2 are two equations and two unknowns. I3 doesn't show there because I3 is already known. It's 2 milliampere. We already got rid of it, and you can see it's a value of 2 milliampere here. So we can keep these two equations, solve them later. Now, if you write the equation for loop number 4, we said it's going to be 2 volts, and then you have here plus 3I4 minus I3 plus 2I4 minus 1 is equal to 0. So we have this equation here for the fourth loop. And this equation luckily does not have any unknowns except I4. So I can collect all the coefficients of I4 and solve for it. I'll get from here that I4 is equal to 1 as shown here. So I4 is equal to 1. And 1 here should of course be interpreted as 1 milliampere because we made this assumption from the very beginning. Now if you solve equation 1 and the equation 2 either using your calculator or using elimination, I multiplied this equation by 2 and then I summed it to this one and this eliminated I1. I was able to obtain I2 as 6 over 7 milliampere and obtain the I1 as 16 over 21 milliampere. Once I have I1, I2, and I already know what's I3 and I4, I3 is equal to 2 milliampere, I4 is equal to 1 milliampere, I am all set to calculate the current going through the resistance R2. Remember that this resistance here R2 has two currents going through it, I2 and I3. So the current going from the top node to the bottom node is I2 minus I3. So in order to calculate this, the drop as shown here with the polarity shown here, positive, negative, as shown here for this figure here, positive, negative. So I can simply have to say that the current going through this resistor is simply equal to I2 minus I3. And this will give me the polarity shown positive, negative as shown here. Okay. So we'll move forward to do the post processing, calculate the current in the resistance R2, and then calculate the voltage across R2. Okay, so you can see here I'm just showing the resistance R2 alone, and there are two currents going through it, I2 from the second loop and the I3 from the third loop. They are opposing one another. Then the current through the resistor R2 is I2 minus I3. I2 is 6 over 7 milliampere as we said earlier. I3 is 2 milliampere. If you subtract these two, you obtain minus 8 over 7 milliampere. Okay. If I need to get the voltage across it, I multiply this voltage here by the resistance value. So minus 8 over 7, you multiply by 2 kilo ohm. Remember, this is milliampere and this is in kilo ohm. So the product will be in volts. So I do not have to write milliampere and kilo ohm because this is 10 to the minus 3 and this is 10 to the power 3. So they cancel each other out. So I just know that my answer will be minus 16 over 7 volts. Of course, as I said in the very beginning, there is no power dissipated in the resistor R1 because R1 is shorted out and the value of the current in this case is equal to 0 watts. Okay, we move to discuss the second question, and this question shows a circuit in a DC steady state, and would like to calculate the voltage VA across the capacitor C4. So I would like to calculate the voltage VA. So this here positive, negative. We're going to call this one here VA, and would like to calculate the voltage across the resistor C6. So here this is one here positive, negative. We're going to call this one here VB. Okay, this is VB, and the current going through the resistor L4, we're going to call it I. So this current here, this is also required. Okay, so all examples that have a steady state circuit analysis, DC analysis, we know that in the transient case, when we close the switch and all these components start to charge, the volt capacitors will take some time to charge, and the inductors will take some time for their current to build up. But once they reach steady state, the capacitors are fully charged. They are represent the open circuit because you don't allow any current to go through them, any DC current. That's it. That is, and the inductors represent short circuit because the current through them is established, and you don't really offer any resistance anymore to the current. So in that case, you have to redraw this circuit again once it's in DC steady state. Replace all capacitors by open circuit, replace all inductors by short circuit, and reanalyze the circuit. And it should be clear that the circuit in the beginning may look complicated, but effectively after we simplify it, it's going to look way simpler. For example, let's take a look here. This capacitor will be, this capacitor C6 here will be open circuit. Okay, so C6 will be open circuit. So this branch is gone, is not there. This C5 will be open circuit, this branch is gone. This C7 will be open circuit, so we have this resistance alone. Okay, this resistance still, the R7 is still with us in the circuit. This capacitor is a very interesting C4. So the capacitor C4 is a very interesting one because what happens is that this disconnects when this one becomes open circuit. This capacitor here, it makes this part here to the right disconnected from the rest of the circuit to the left. Okay, so and this resistance here R6 will be hanging in the air. We have this resistor is in series with this one, in parallel with this one. This inductor now is short circuit, so it's not there. This is open circuit because of the capacitor. These three represent short circuit. Why? Because the inductor is going to short out the capacitor and the resistor. So this is short circuit here. This capacitor has been also eliminated because this inductor represents short circuit. I can replace this current source with the resistance across it just to make things easier by a voltage source in series with the resistance. So the voltage source will be 20 volts, this product, and the value of the series resistance is 1 kilo ohm. So I have here 1 kilo ohm in series 1 kilo ohm will give me 2 kilo ohm. So the circuit effectively, after you simplify it, you will have this current source, you will have this series resistance, you will have R7, this will be to the right, and then to the left you have this resistance hanging from the air. You have this resistance in series with this one and this one in parallel. Okay, and you have this all is not there, this are not really there. You have one resistance, a second resistance, and two voltage sources in series. So you can redo the circuit with great ease. It will have actually very little components, but you have to keep track of the responses you are looking for. I need the voltage across the capacitor C4, so I need to calculate this one. Okay, I need to keep track of the voltage across C4. I need to keep track of the voltage across C6. I need to keep track of the current through the inductor L4. So even though these capacitors and the inductors will disappear from the circuit, but I have to keep track of the voltage across them. And once I know the voltage and current through them, I can calculate the required energies. Because the required energy of the capacitor is 1/2 the value of the capacitor multiplied by the voltage across it squared, and the energy stored in the inductor is 1/2 the value of the inductance multiplied by the current through the inductor squared. Okay, so I redraw the circuit, and after I draw it again, it becomes extremely simple actually. This is the voltage I'm looking, this is the voltage VB I'm looking for. This is the voltage VA I'm looking for. I call the voltage of this point relative to ground as V1. I call the voltage at this point relative to ground as V2. So VA is nothing but V1 minus V2. Okay, and I replaced all the resistances. Here we had 3 resistances, if you remember. 1 resistance in series with 2 in parallel. I got the equivalent value, and this 1.75K. I got rid of the current source, as you could see here. The current source now represents a voltage source of value 20 volts and a resistor value 1 kilo ohm. So now our target is to do regular DC analysis. The inductors are not shown because they are all short circuited. The capacitors are not shown because they are all open circuit. And we just want to find the voltages VA, VB, and the current I. I is not shown here in this figure. After I found the current I note, which is shown here, after I found the current I note, I'm going to use this current and split it between the 2 parallel resistances. I will show this as a post-processing. Just remember that this 1.75K is actually the result from combining 3 resistances. One resistance in series with 2 resistances that are in parallel. So now let's try to analyze to get the voltages V1 and V2. V1, remember there is no current in the 2 kilo ohm, so V1 is the same as the voltage at this point. Okay, the voltage at this point is simply a voltage divider. I have 30 volts, the sum of these two. This is 1.7K, and you have 2 more resistances, 1K and 1K in the loop. Then as a voltage divider, I can simply say that V1 is equal to 30 multiplied by 1.75K over 1.75K plus 2K. So I applied voltage division around this loop. I have a voltage source of value 30 volts, and I have resistance of 1.75K. I need the voltage across this resistance in comparison to the total resistances, which are 3.75 kilo ohm. So once you do that, you calculate this one, you get that V1 is equal to 14 volts as shown here. Okay, so V1 will be equal to 14 volts. This will be our first step. Now I need to calculate the voltage V2. Remember, you have a current source. This current flows in this loop here, and this loop is disconnected from the left side of the circuit. So the voltage V2, if you notice the polarity as which this current is flowing, will have this polarity here, positive, negative. Okay, so I can simply say that the voltage V2 is equal to the current 5 milliampere multiplying the 1K, so it's going to be equal to 5 volts. So this one here relative to ground is 14 volts. This one here relative to ground is 9 volts. Then VA, which is V1 minus V2, is equal to 14 minus 5, so it's going to be equal to 9 volts as shown here. If I want to get VB as well, and I'm looking for VB, VB is the voltage across the current source, which is a voltage across this resistance as well, which we just calculated, which is V2, is equal to 5 volts. So I already know what is VA, I already know what is VB. Can I get the current I note? Of course I can get the current I note. I know the voltage V1 is 14 volts, okay? So 14, I'm going to divide it by 1.75K. This will give me the current I note. And then I will split I note to get the current I going through the inductor. Remember, this branch had 4 components. One resistance in series with a resistance which is in parallel with a resistance in series with an inductor. Okay, so I'm going to now use current division in order to calculate the current I from the current I note. So I'm showing here in this figure only the branch that contained the 3 resistances. So this is the 1K in series with 3K in parallel with 1K and the inductor. So I have already calculated I note here. I can calculate I note. The voltage between V1 to ground is 14K, and the total resistance between here and ground is 1.75K. Then the current I note is equal to 14 over 1.75K is equal to 8 milliampere. So this is the current I note, but I'm not looking for I note. I'm looking for the current I. Remember, the inductor represents short circuit, so I need the current going through the 1K resistor. So I'm going to multiply, I'm going to use the current division rule. So the current I is equal to the current I note multiplying 3K over 3K plus 1K. Okay, and of course the inductor does not count because it's simply short circuited. So I am able now to calculate that I will be equal to 6 milliampere as shown here. So this is what we have here. I is equal to 6 milliampere. Now once I know the current I can get the energy stored in the capacitor C4. I know the voltage VA is already, we calculated that already, is equal to 9 volts. Okay, so I can simply say the energy here is 1/2 C4 multiplying VA squared. So C4 is 2 microfarad. We calculated VA to be 9 volts. So you multiply this one and you square, you get 81 microjoule. If you want to get the energy, the magnetic energy, this electric energy stored in the capacitor, this is the magnetic energy stored in the inductor, and is stored in the magnetic field of the inductor. This is really what's happening. So this one here is stored in the electric field of the capacitor. This one is stored in the magnetic field of the inductor. 1/2 multiplied the value of the inductor multiplied by the current going through the inductor squared. So the inductor we can calculate the value here. Let me see. So this is the value of the inductor. I believe I'm missing here millihenry. I believe so. This is the value of the inductor. Okay, and this is the current that we have. It's 6 milliampere. So 6 milliampere squared. Okay, so whatever I'm gonna get from here, I think I'm missing 10 to the minus 3. So if I have to correct this one, this is gonna be probably 10 to the minus 6. Okay, the reason for this is this one here is missing 10 to the minus 3 because this is 120 millihenry. 120 henry is a huge inductance. It's not really a practical inductance. 120 millihenry is a more reasonable one. So we multiply the value of the inductor in henry, okay, which is this one here. We multiply by the current squared, okay, and then we sum all the components and we obtain 2.16 microjoule. Of course, the unit of course here is joule, so everything will be microjoule as well. Okay, so this is how to analyze these circuits in DC. Consider all capacitors to be open circuit. Consider all inductors to be short circuit. Keep track of the voltages and currents that you want to calculate. Do regular DC analysis and then try to recover the voltage across each capacitor and the current through each inductor.